Unit 2C, Lesson 4, Comparing Linear and Exponential Models. We're also going to include quadratic functions. So given a graph, you need to be able to determine which type of function that's referring to, come up with the equation. We're also going to focus more on recognizing exponential graphs. The first thing we need to discuss are the general graphs for the exponential function. So our exponential function is f of x equals a times b raised to the x power. B is referring to our growth factor. That tells us whether it's exponential growth or exponential decay. Think about the story problems we talked about earlier in the year. If the value of a is greater than 0, meaning it's positive, then our graph is going to be above the x-axis. Our function values are going to be positive. If our a value is less than 0, so that a value is negative, then our function values are going to be below the x-axis. Once we have that narrowed down, if b is greater than 1, so we have exponential growth, then as we go from left to right, our graph is going to increase, and it's going to start increasing very rapidly. If our value of b is between 0 and 1, as we go to the right, our graph is going to start to decrease. If a is less than 0 and b is greater than 1, as we go to the right, our graph is going to start decreasing, and it's going to start decreasing very rapidly. If a is less than 0 and b is between 0 and 1, then as we go to the right, our graph is going to start increasing and level off as it gets closer to the x-axis. So you need to look at the value of a to determine whether our graph should be above the x-axis or below the x-axis. Then we have to look at the value of b to see if our function values are going to start increasing very rapidly or decreasing very rapidly, or if they're going to start leveling off, approaching the x-axis. In the first example, we want to use this graph to determine which equation represents this graph. First, we have to recognize the general behavior. We have a corner or a v that is formed, so we know it has to be the absolute value function. So right away I know it's not going to be option 2, it's not quadratic. Then we have to use what we talked about in lesson 2 when talking about those transformations of the graph, understanding our horizontal and vertical translations and how those are going to be inputted into the graph. So first thing I notice is I have a vertical translation 1 unit up. So at the end of my equation, I should have a plus 1 at the end. So I know it's not equation 1. We already got rid of equation 2. Equation 3 is not going to work because they're subtracting 1, so it must be equation 4. If my pen would work, we have equation 4. We have a vertical translation up 1. We have a horizontal translation 3 units to the right. Second example, very similar. We want to look at the graph, determine which equation represents the graph. We have a parabola in this case, which we know is the graph of a quadratic function. So right away we can get rid of option 1. This is an exponential function. So it's either got to be 2, 3, or 4. The next thing I notice about this graph is that it forms a frown face. So it's upside down, which means my a value must be negative. So that eliminates option 2. And that eliminates option 3. Well, option 3 isn't even a quadratic, that's a linear, so that one would not work either. The only logical option is option 4. This is a quadratic with a negative a value, which means it is going to open down. Now to example 3. This is going to be our first exponential graph. As we continue to the right, this is going to get closer to the x-axis. It does not come back up, so this is not a parabola. It cannot be a quadratic function. So right away we can get rid of option 2. Next we have to look at our function values. I notice my graph is above the x-axis, meaning my function values are positive, which means the a value on my exponential must be positive. So that narrows it down to option 1 or option 3. Option 4 is not going to work. I have a negative 1 for my a value. So now how do we determine if it's going to be equation 1 or equation 3? Before, at the beginning, when we had that table referring to the different types of exponentials based on our values of a and b, we did not refer to what happens if our exponent is negative. So how is that going to affect the graph? Okay. Well, let's just plug in a couple points. If we would plug in 0 for x, and we're comparing our two different graphs, y equals 2 to the x, and we're comparing y equals 2 to the negative x. If I would plug 0 in for x, well, anything raised to the 0 power is going to be 1, and that's going to occur in both of these. If we have an exponent of 0, we have a y value of 1, which is why we have that location on our graph of 0, 1. Well, what happens if I plug in 1 for x? If I plug 1 in for x here, I have 2 to the first. So my value, if I go to the right with my x values, my y values should start getting larger if my equation is going to be y equals 2 to the x. Imagine plugging 3 in for x. 2 cubed is 8, so if my x value is 3, my y value would have to be 8, my graph would have to be up here. So I can determine that it's not going to be the graph of y equals 2 to the x. It must be the graph of y equals 2 to the negative x. Let's think about, why do these values make sense? Why is the graph going to start decreasing as we go to the right? Well, now we're going to bring in topics that we talked about earlier in the year when we talked about properties of exponents. If I have a negative exponent, I can rewrite this so that it has a positive exponent by taking the reciprocal. So this would be the same as 1 over 2 to the positive x. Now if I plug in that value of 3 that I tried before, 2 cubed is 8, but that's in the denominator, so now that would be 1/8. My graph, as I go to the right, because now my exponent is in the denominator, my y values are going to start getting smaller. They're going to get closer to that x-axis. So now we have a different type of example. We have a table of values. We have our inputs x, and we have the outputs f of x. We want to match these table of values to the correct function down below. The first thing we can do is narrow some options down based on the input and output. So what I look at in the table is my increments. For my x values, I went from 3 to 4, which was a change of 1. When I increased by 1, my function values increased by 8. So now I'm going to compare 6 to 7. And the reason I'm skipping to 6 and 7 is because my next increment goes from 4 to 6. That's not a change of one value. I want to make sure I'm changing by the same x value. When I go from 6 to 7, which is a change of 1, just like 3 to 4 was, notice to go from 65 to 129, that is not a change of 8. So over the same interval, I do not have the same difference, so this cannot be a linear function. This cannot be option 2. This cannot be option 4. I don't have the same differences over the course of the same interval. So I'm either going to be option 1 or option 3, which implies that this is going to be some sort of exponential graph. So what can we do? Well, we can plug in a couple x values and see if that works in the equation. If I plug 3 in for equation 1 and for x in equation 1, 3 cubed is not going to work. That's going to be a value of 27. If I plug 3 in for x in equation 3, 2 cubed is 8. 8 plus 1 gives me 9. If I would plug 4 in, 2 to the 4th is 16. 16 plus 1 gets me 17. So the correct answer is going to be number 3. So when you have these table of values, look at successive differences in your x values. Make sure that correlates to the same difference with your function values. That determines whether or not it can be linear. Then you can narrow down your options from there. Now to the last example. As x increases beyond 25, which function will have the largest value? So our first equation, we have an exponential 1.5 to the x. The second one, we have a linear 1.5x plus 3. The third equation is a quadratic 1.5x squared. And then the fourth one is what's called a cubic function. It's a type of polynomial. We'll get to that later. 1.5x cubed plus 1.5x squared. So as values of x go beyond 25, they start getting very large. which function is going to have the largest y values. Okay, and we can narrow this down a little bit, because if we have x raised to the third power, think about if we put 25 in for x. 25 cubed is going to be larger than 25 squared, or just 25. So we know that the fourth equation must be larger than the second and the third equation. So we can ignore the second and the third. A value, a positive value, beyond 25 raised to the third is going to be larger than if we square that value or raise it to the first power. So now we have to determine, is 1.5 raised to the x, an exponential, going to grow more rapidly than something raised to the third power? And this is a fundamental connection difference between polynomials, which linear, quadratic, and cubic are. Those are types of polynomials, and the difference between those and exponentials. And that main idea is that as values of x get very large, exponential equations are going to start growing more rapidly than polynomials do. That includes linear, quadratic, cubic. Exponentials are going to grow more rapidly.